Alright everyone, now let's take a look at this Euler-Mascheroni constant here. I'll actually get this pen out. A certain kind of pen. So we have this Euler-Mascheroni constant. And it's defined by this image, which I have right up here. The sum of the inverse of all natural numbers, so right here. And this sum, by the way, is going to be very important later in the video. And it's this basically arbitrary sum. This is known as the harmonic series, actually. If we take the sum from 1 to n of 1 over k, so the inverses of all the natural numbers, minus ln n. Alright, so now we're making sure that n approaches infinity. So n is basically some arbitrarily large value. You can think of it as a million or a billion or a trillion, or, well, in reality it's growing larger than that. And we're using that as our boundary for the sum. And the sum itself is really the harmonic series, and there are a couple interesting points about that I'd like to make. The harmonic series actually is divergent, despite what you might think. It doesn't actually converge to a finite value. So that's what kind of makes this so interesting. Once we apply the minus log n, that's what makes it convergent, right? That's actually what converges to the Euler-Mascheroni constant here. And I have the first 25-ish digits from Math World of this constant. And we don't really know that much about it as mathematicians. That's one of the most important things, one of the most amazing things. We don't know if it's irrational. We don't know even if it's transcendental. And that's just incredibly interesting. It's typically represented by this Greek letter gamma. That's where you'll see it in many different formulas and equations, stuff like that. But, few people know about this, but it's still interesting. It's still something worth talking about, something worth spreading, right? It's incredibly awesome to think about. It's just this pure number which we're defining. It's a harmonic number minus log n as n approaches infinity, right? So that's quite cool. And one of the things I did, just to show you some details about this, is I actually wrote a Java program, which you can see right at the bottom, and it returned the approximate value. I guess it's to the first maybe 6 or 8 digits of this expansion, basically. So it's just kind of cool. And I made this note here that as for that arbitrarily large index, I use the number 1 million, right? So that's my large kind of boundary of the sum. Let me make sure that's highlighted. Right. That's what this means. I'm not sure how many of you are familiar with Java coding, or Java programming, but it's, index is less than n, so I'm going from 1 to n, essentially. Technically, I guess this is, less than, so it really just counts for 999,999 iterations. But my point is, by about 1 million n iterations, h sub n, meaning the harmonic sum, the finite sum, is still less than 14.4. And you can see, as I'm showing you this, you can see the clip of me running it. At first, you might actually think that it converges to some finite value, right? I mean, it's only 14.4 after 1 million iterations, but indeed, it is actually provable that this sum is divergent. That's the key point. And another interesting fact about this series, which I've kind of circled at the top, it's special in many different ways. You'll find that in mathematics. In fact, you can generalize it in order to get the Riemann Zeta function, basically. The sum from k equals 1 to n of 1 over k to the s for some complex exponent, and that's incredibly interesting. And we'll get more to that later, I promise. But even separate from that, if we use this particular case where the exponent's 1 and we get this divergent series, well, another interesting point is that this sum is actually non-integral. And that might also surprise you. Because basically, if we take this sum out to any number of iterations, Let's say n is 10. Let's say n is 100. Let's say n is 6,789. Something like that. Or any natural number for that matter. Wherever we stop, we know that that number is not an integer. Isn't that so cool? Doesn't that blow your mind? I mean, this is like, we know the series is non-integral. That's provable. I must say I apologize. I don't know the exact proof of it. I don't have it in my mind right now. But there are other things I need to get to. But if it's something you're interested in, let me know and I'll consider proving it in a future video. But imagine that. I mean, it's divergent non-integral series. Just plainly amazing. I'm gonna move on now. And you know, this really is just one individual case of this larger presentation here, which describes Logarithmus Naturalis. Basically, we're gonna study the applications and appearances of the natural logarithm function. And you see a couple pictures up there describing, you know, what the natural logarithm actually looks like if we plot it. It's really cool. I appreciate you watching, and I hope you enjoy this. And you know, you may already know I'm not too big a fan of applied mathematics, but nonetheless, this is some pretty interesting stuff. I must admit there are valid applications of mathematics. You know, you shouldn't be neglected, I suppose. But here we have this first example, which is pH, and for those of you who like chemistry, I'm sure you'll enjoy this. Basically, we have this formula here, which is the negative log base 10 of the concentration of hydronium ions, and that's in moles per liter. Now, it's been a while since I've taken a chemistry course, but I remember doing a few problems with this. I wanted to give you a general graph of this, the log base 10, and you know, this is only a section of the graph here, so I thought, I was just thinking to myself, there is actually a possibility that the function can be negative. In fact, we can, even after substituting in this equation, we can actually have negative pH. That's something which many people might not know, you know. Typically they see values of pH within the range like 1 to 14 or 0 to 14. But indeed, you can actually have a negative value returned. And that is basically if and only if the concentration of hydronium ions is so large that it's greater than 1 mole per liter. It's kind of, might be hard to wrap your head around, but if the concentration is extremely large, that means the substance is extremely acidic. And if we were to show that in our plot, we can see that the function can indeed be negative. It can go into this negative range values, you know, for pH. It's pretty cool, and I thought I'd give you a more broad representation of this graph, if possible. So just show you that it curves in this kind of fashion, this negative logarithm. It's pretty cool. Anyways, moving on, we have a few other applications I wanted to describe, like decibels, basically giving you the sound intensity, or the loudness of a sound. It's 10 times the log base 10 of this ratio, where the ratio is one intensity versus the what's called the threshold intensity, something barely audible, right? So, and we have a graph to the right. That's just wanted to give you a cool graph, because who doesn't love logarithms, as I said before? It just grows logarithmically, and it's interesting, purely interesting. And you know, this is, you know, pretty cool. And if we have the Richter scale, that's actually a very similar equation, just log base 10 of this similar ratio of the intensity of some kind of tremor or earthquake, which would be measured in the ground, you know. So, and I thought I'd give you maybe a slight example of that. Let's say we had a 4.5 magnitude earthquake or something like that. That's generally what's considered to be a moderate earthquake. It's kind of to the lower end, but I just thought as an example, we would solve for the intensity, basically. And to do that, we just raise 10 to each side of the equation, essentially. So we get I over I naught. So that ratio is equal to 10 to the 4.5, which is really around 31,000, as you can see. 31,600, whatever, times the threshold magnitude, intensity, essentially. So that's interesting. We think of these things on this Richter scale, and we say 4.5 magnitude. Well, that turns out to be 30,000 times the intensity of, the smallest one. It's something interesting to think about. And lastly, we have this Tsiolkovsky rocket equation. Now, personally, I'm not really an aerospace engineer or anything, but I've heard of this, and this is actually an application of the natural logarithm. Which is arguably even more interesting in pure mathematics. And we see the nice formula right here, a formula for del V. I don't know what all of this means, but it's a natural logarithm. It uses a ratio of masses. It uses some specific impulse and things like that. But I say enough of these applications. We need to get to some of the specific facts on one of my favorite numbers, and that is indeed the natural logarithm of 2. And we see the expansion right here, 0.693147, and it keeps on going, 105599. I would actually very much recommend to all my viewers, whether you be math majors or engineers, math enthusiasts, scientists, or economists, really whoever you are, that you memorize a few of these digits of the natural logarithm of 2. It's really an underappreciated number in mathematics, in my opinion, in my limited experience, but especially in society. I mean, people recognize pi and sometimes even e, but very rarely do they give credit to the natural logarithm of 2. And I'm going to show you why this number is interesting. The first one is economics, and what they call the rule of 72. Now, people typically say for this rule of 72, it's an estimation of the doubling time for some interest that's being compounded, especially if it's being compounded continuously, even if it's not. We're supposed to give you an estimation of the doubling time if you know the percentage rate of some fund involving interest. So we have this derivation on the left, and that's a bit of a more general case. If we have some rate r, and assume that's in decimal form now, and t is going to be our time, which we solve for, actually. And we'll say p is our principal value. We want to set it equal to 2p, so we're going to solve for the time it takes to become double what it currently is. So now we can cross out the p's at this point. It doesn't actually matter what we start with. We get a 2 on the other side. We get a ln 2, which is interesting. And we divide by ln 1 plus r. Now that's pretty cool. But an even more interesting case, even more specific case, is if it's compounded continuously. So it's like constantly compounded, is how you can think of it. On the right, we have this more specific case, as I was saying, p times e to the rt. So e, many of you will already be familiar with, that represents the continuously compounded interest. And you can see some other videos. I'll probably link to them in the description, if you don't exactly know where that comes from. But we use e, that transcendental constant, for continuously compounded interest. But I'm kind of digressing. We cross out the p's, we ln both sides, we divide by, in this case, it's simply r. And that gives us our doubling time. So it's log 2 over r. Well, that's very interesting. What that actually equals is 0.693147, 1806 approximately, divided by the rate. And if you want to convert this, because people typically think of rate as in a percentage, then you can just multiply by 100 over 100, and we get this equation down here, at the very bottom. This equation. And, rule of 72 is what people mean by this, but it's kind of my argument that people should give more credit to log 2. I know people say 72 has more, integer divisors or whatever, but the idea in theory of log 2 is actually quite interesting. 69.3147 divided by the rate. That gives a more precise approximation also of doubling time. So it shouldn't be neglected, in my opinion. Now, furthermore, in this second example, we actually have a bit of a music theory analog kind of thing. This is a bit forced, I know, because technically it's kind of log base 2, but yeah, whatever, no one cares. You should actually see my other video on music theory. Well, it's really just basic. It's about musical tunings, but you should see that. I'll link to that. But we basically have 1200 over the log base 2 of the natural logarithm of a frequency ratio. And that, again, assuming 12-tone equal temperament, which is the most common system in modern music, it returns the number of some interval. And it's related to sense, which is a measure of interval, basically, based on pitch and things like that. And it's all assuming 12-tone equal temperament, which is just one way, just one system of doing things. I'd like to emphasize that. But, moving on. We have some relations to the Riemann Zeta Function. Now, I mentioned this earlier in this video. You may remember that. This one right here, this sum which you see, S sub n, word on the street has it that this sum approaches log 2 if we take it out to infinity. Right? So that's quite interesting. I decided to test that myself with a Java program. You can see this. N, in this case, is this arbitrary large index. Now, I have a reason. I'm going to tell you up front. I have a reason for just calling it 56. You're probably thinking, 56? Why? That's just what? Like 7 times 8? That's not a large number. That's not infinity. Right, well, that thing right there, that number, N, as I kind of have it, as that arrow, I'm just specifying that's going to infinity. But really, I chose 56, and that's pretty important. I added a bit of an animation. Well, a couple different animations. But it's arbitrarily large, and 56 in my case, because there was actually a precision loss after k is approximately 54. So I wanted to account for that. And you can actually see on screen now another example of me running this program in the console, and you can see how it kind of ended that precision after 54. It kind of got, I was using doubles in this Java program, so it kind of just became meaningless if we kept going after 57 or some number close to that. So, and we see here, I'm not exactly sure. I don't need you to be completely familiar with Java programming. Personally, I find it interesting. But we have different methods here. I made a method for the zeta function, indeed, right here. And this upper index, I say, within this function, I declare a new n less than about 150,000. And it does make a difference on the accuracy. So that's just something to think about. We got to make sure that zeta function is precise enough. And then we perform some operations. And imagine that, we divide by 2 to the k. That's interesting. Again, I'm not sure of the proof of this. So I apologize that I don't have a proof. Someday I hope to get back to you in some new video about log 2 and the zeta function. Because there are many actually interesting properties. So if you'd like to look up more in your spare time, I completely encourage that, actually. Or if you can direct me to a proof, even better. But I mean, we're all learning together anyways. But my point is, I ran this Java program, as you were just watching, and ultimately I got this value, precise to, I think, about 5 or 6 digits, of what is essentially the log of 2, excuse me. So 0.69314, and that day kind of, became less accurate after that. 718, we didn't really get there, we got 551, but, you get the point. It's really the limit as n approaches infinity. It's kind of a speculative, like, this is what would happen if we could go to infinity. Yet another interesting part of the natural logarithm of 2, one of my favorite numbers. I can't emphasize that enough. But moving on, we have this final, very interesting fact about the natural logarithm, and that is its sum using Maclaurin series. Alright, now I'm going to piece together this proof for you. I took a picture in real life, and I'm going to kind of piece together this photograph, and it'll all make sense. So we start with this basic formula for the Maclaurin series. Now, if we have some function, some f of x, that isn't a polynomial, so presume that it is kind of loosely defined as a transcendental function, which we don't really have a polynomial approximation for yet. Well, we can apply this formula, depending on what it is. We can't always apply the formula. But this nice Maclaurin series, we can apply it in order to find our polynomial approximation. So, for the function ln of x, I'm sure you're already jumping ahead and saying, well, now, hang on, this formula says f at 0, right? And f prime at 0, and all these 0 substitutions. Well, ln of 0 is pretty much undefined, right? And you'd be absolutely right. That is the reason we're actually going to kind of change it up a bit and instead use the ln of x plus 1 as our f of x. And you can see that right here, which is pretty cool. Yeah, it kind of avoids that uncertainty with ln of 0. But, you know, let's move on. Let's not just end there. We find a way as mathematicians, so we can substitute 0, and, you know, we should actually think about this as a whole, and really we realize we're going to use the derivatives of ln of x, and in order to do that, I listed them out for us right underneath here. And so the first derivative, unsurprisingly, is 1 over x plus 1. Now, that's interesting, though. We shouldn't take that for granted, and we should appreciate that. The derivative of natural logarithm is a rectangular hyperbola. Now, that's amazing. I mentioned that in my part 1 of this video. But anyways, moving on. We have the second derivative, so we bring down the exponent. We can apply the chain rule here. It's really just times 1, so it doesn't make too big a difference. And we decrement the exponent, so it's negative 2. And this is just some basic calculus. We apply the derivative again. We get positive 2 times quantity to the negative 3. Then we get negative 6 times quantity times the negative 4, or to the negative 4, etc., etc. And so we find, after doing this, that these coefficients, and I'm actually probably gonna draw a little bit here, just to show you the coefficients here. We have 1 here, negative 1 is coefficient here. Just want to emphasize that. We have a positive 2 here, a negative 6 here, and eventually, if we keep continuing this, we're going to bring down the exponent. So we'd have it times 4, and then decrement it, so it'd be, well, times negative 4. Times negative 4, and then we decrement it, so we get negative 5. So I just wanted to show you that. And if we did it again, we'd multiply by negative 5, decrement the exponent again, multiply by negative 6, decrement it again. You know, we'd follow the same kind of algorithm. And that's all fine and well and good, but we're noticing probably the pattern that the coefficients are really the quantity n minus 1 factorial, which is quite interesting. It also happens to remind me of the gamma function, which you can see. But, anyways, I'm a bit digressing at this point. We're just kind of noticing the pattern that comes about for the coefficients. Also, another thing to note about this, we say f at 0, right, and f prime at 0, f double prime at 0. That's really our main focus, as I mentioned before. Well, if we substitute 0 in for x in any of these derivatives, we're going to get 0 plus 1 to some negative power. Well, that's really just 1 to a negative power, so we can essentially neglect everything else there. All that really matters is the numerator, which are these coefficients, as I mentioned. That's really very special, very important in this case. So, you know, without further ado, without further me blabbering on, I'm just going to piece together this part of the proof. We have ln of 1, well, that's kind of the most basic thing. We have ln of 0 plus 1, and that is, in the conventional sense, 0, so we can neglect it, plus 1 times x. Now, this is a result of what I just mentioned, because it's just the coefficient that matters. Well, the coefficient in this case is 1, so that's alright, minus x squared over 2. Now, in this case, we need to think about this a bit more, because with this term here, we're dividing by 2 factorial. That's actually the real truth. That's really the kind of the meat of the Maclaurin series. We're dividing by n factorial. So I'm actually going to write that up here. It's f to the n. It's the nth derivative of f of x. Can't talk. Times x to the n over n factorial. That is the typical Maclaurin series approach to a function. That's supposed to be a 0. Sorry, I'm just trying to do this with a mouse. It's not always the easiest thing. But yeah, we have and this is the general formula. The more general formula for a term of the Maclaurin series. So, and I just told you that the only thing that really matters of this, the nth derivative of f at 0, is really the numerator. And the numerator, I also just said, was quantity n minus 1 factorial. And so why am I saying all this? Why am I doing all this? Well, the reason is really that n factorial can be thought of as n minus 1 factorial times n. So those two cross off, essentially. The point is, we end up with n in the denominator, and that's very interesting. That's where this is going. And so our final sum, after doing this wonderful, neat work and everything... Oh, I hope it was neat. I tried to make it neat. I meant the maths was cool, not that it was... Right. We get this final step here, and we're given, if we want the f of x, so the Maclaurin approximation to the natural logarithm of x plus 1, we get this whole thing. X minus x squared over 2 plus x cubed over 3, and without further ado, we substitute 1 for x, and then that's ln of x plus 1 being the ln of 2, and then we simply, it all simplifies, and it looks so wonderful. It works so elegantly, right? We have ln of 2 equals 1 minus a half plus a third minus a fourth plus a fifth minus a sixth to infinity, right? That's amazing. That, my friends, that is the infinite sum approximation of the natural logarithm of 2. It converges to the ln of 2, and we know that. We know that for sure now. That is amazing. And I have a few final words on this topic. Are we people to take these things for granted? Nay, we must, I say, must, maintain our interest in finding and searching for truth in mathematics. This is something very important to me. It's something for which I have much passion, and I'd like to share these elegant topics of mathematics with the world. So, thank you very much for listening, and I'll see you another time. Please subscribe for more.